Hello, I'm Muhammad Yasir Zakaria from class TO4 and this is my EM3 assignment on Euler's method. So, what is Euler's method? It is an estimate for the solution of a function where it's really hard to find the exact solution, so we approximate it instead. So how does the formula work? So the general formula is as follows: y1 equals to y0 plus the product of h and f prime x. So our h here is the step size or the increment along the x-axis, and our f prime x is the derivative of x. So how is the formula derived? So first we will take the linear gradient formula y equals to mx and we will modify it a bit. So y equals mx can be written as y1 minus y0 equals to m times xy minus x0. So xy minus x0 is actually our step size h, since it's the increment along the x-axis. And our m is our gradient, which is our derivative, so it can be rewritten as f prime x. So we will get y1 minus y0 equals to f prime x times h. So since we want to find y1, we will move the y0 over to the right hand side, which will give us y1 equals to y0 plus f prime x times h. So here we have two curves. The blue line is from the Euler's method and the white line is the actual function. So from starting point x0, y0, we move a step size of h along the x-axis to x1. As you can see here, to find the approximated y1 value, we are using the gradient equals to rise over run formula. So the rise here is our gradient times our step size or our run, and that's how we find the rise value or our approximated y1. So we will add that value with our y0. So now we will be attempting to solve the IVP or approximate the IVP using the Euler's method. So our goal is to find the approximate value of when x equals to 1. So I have three columns here: x of n, y of n, and dy dx, or f prime xy. So for the x of n, we start with the initial condition when x is 0, and we increase by step size of 0.1 all the way until when x is 1. And for y of n, which is what we are attempting to find, I've used the Euler's method formula, which is the previous y value added with the product of the step size, which in this case is 0.1, and the previous derivative value, which in this case is 1. And for the dy dx, I've used the given equation here, x squared plus 1 over y equals to dy dx. So I've used the x squared plus 1 and the whole thing divided by y. And so I've used these formulas for all of the cells all the way until we reach when x equals to 1. And so we will reach an approximate when x equals to 1, y equals to a value of 1.9114. So for the final part, I've used calculus. I've used a separation method to find the real value, and I've got 1.915 as the real value. So here I've used the Euler's method thrice, each with varying step sizes, and what we can observe is that with a smaller step size, the approximate y1 value is much closer. It's much closer to the real value. And so as we can see, the approximate error for smaller step size is smaller. Thank you for watching. See you soon.